in this slide. So basically, the reason that we have this body spike is because there are this inductor, right? So if we can, kind of lower this inductance, then we will able to lower this voltage peak. So what primary clamp do is, so basically we are adding two diode on the primary side, and instead of only using one LS, so we kind of split it. So in the previous slide, this LS can be transformer leakage inductor, doesn't necessary to be a separate inductor. But in primary side clamp, we do need to have external inductor, so that use this energy in this inductor for the self switching, and then we can kind of try to minimize the leakage inductor, so that only the leakage inductor is resonant with the COSS and causing that ringing. Okay, so basically you can see this waveform, right? So the blue one is if we so the total series inductor will be 4 microhenry. So if we move the 3.5 microhenry to this LS as an external inductor while minimize the leakage inductor to 0.5 microhenry, then compared to we don't have the external inductor, the voltage stress will be very much limited. So that's the the other way we can lower the rectifier voltage stress with a primary clamp. But the drawback is you will need additional components, two diode and the external inductor. Okay, so here's a third way that you can do for clamping the output rectified voltage stress is you add the active clamp leg to the output rectifier. So basically, there's a FET in series with a capacitor. So when there's a voltage stress happen, on the output rectifier, the current, there will be a current flow through the clamping cap and the body diode of this MOSFET. Then that way you can clamping the voltage rectified voltage stress to the CCL. And then because for inductor we need a voltage second balance, for capacitor we need a current second balance. So you have current flow through this direction, then there will be a current need to flow through the other direction to maintain the capacitor, energy balance, right? So what we need to do is, so when the voltage spike happen, the current will conduct through the body diode of the clamping FET, and then within the body diode conduction time, we need to turn on the clamping FET before the current goes to the other direction. So that's basically the idea of the active clamp. So the only thing is, and the equation here shows that you need to design the CCL capacitance to be much larger than the switching period, so that the ripple on the CCL is not too large, right? Okay, so one thing you can notice that with the active clamp, the current, after we add the active clamp, the SR current and also primary side current is got distorted. So it's no longer monotonic ramping up in this period when the active clamp is working, right? So if we are doing a peak current mode control, we want to expect the current to ramping up monotonically, but in this case, in this active clamping operating area, we are not able to do a peak current mode control. So that means we'll try to minimize the pulse of the clamping fed, so that after the clamping fed is turning off, we still have a long duty cycle area. We can control this phase shift full bridge converter with peak current mode control, right? So that's one reason we want to minimize the time, the conduction time of the clamping this clamping fed. So notice that if you increasing the clamping fed conduction time, the clamping capacitor voltage will be even lower, but then your controllable range for peak current mode control will be smaller. Also, if the active clamp leg conduction time is longer, then the IMS current on this fed will be higher. So basically, in our design, we only need this fed to conduct 300 nanoseconds, which is pretty short. Okay, so let's talk about the operation, output rectifier, voltage stress, and the clamp. And now let's talk about control. So the basic control for phase shift full bridge is the voltage mode control. So basically, there's we will compare our feedback voltage with ramp voltage, and depends on the the comparison result that will determine the duty cycle, the phase shift value of the output, right? And through the T-type flip flop to generate the secondary side back and to do the control. So one thing you can notice that yeah, we will talk about it in a later slide, but here you can see we insert a blocking cap here to maintain the 40-second balance on the transformer for voltage mode control. Okay, so we just talked about voltage mode control. It's quite a general control method and most straightforward and easy control for phase shift full bridge converter. And there are people adding the input to input feed forward, so that these phase shift full bridge converter can have a better I would say light transient response, input transient response. And the most people prefer to use control method right now nowadays is the peak current mode control. Basically, we will add the current sense circuit device in the circuit, and based on this current sense information, we can compare with the target feedback voltage to determine what's the phase angle need to be. And to do that, they will provide us a very fast and response to the current. So here, just a quick comparison between voltage mode control and peak current mode control. So voltage mode control, because we are not sensing current, we are not control current, we are only just sense output voltage and feedback and do a generate duty cycle. So if the current is unbalanced, if the duty cycle is unbalanced, then there will be current imbalance on the transformer. So there's no way, if we do this control and to maintain the transformer body second balance. So that's why we will need to add a blocking cap to make sure the transformer only see AC voltage. So the drawback of adding a blocking cap is, that will increasing the output rectifier voltage stress, because originally the voltage applied on the primary winding is just the input voltage, right? But now it's input voltage plus this blocking cap voltage. So this blocking cap voltage is a ripple, so you will basically add the input voltage times turns ratio times the ripple of the blocking cap. So the voltage stress on output rectifier will be higher. Okay. And so for picker mode control, we'll need to sense the inductor current or transformer current somewhere in the phase shift full bridge converter circuit. So generally, there are people usually sense the current in one of these three locations. So there are trade-off between those locations. So if we put the current transformer in location number 1, so the current transformer can reset itself easily. But the problem is the current here, it will contain no DC current information. So if the transformer is actually imbalanced and with a DC component there, sensing number 1 will not tell us that information. So number 2, we are able to sense. So number 2 is at the input bridge, either the ground side or high side. So we are able to sense the DC information there, but then from the input there should be a bulkhead to the full bridge. There's probably a bypassing ceramic capacitor. So if you put some sensing circuit here, they will adding inductance there. So that inductance will making the sensing signal distorted, right? So that's a challenge, in layout if you want to put it there. While it's it's very easy to put the current sense device in this location. So number 3 is also possible that in number 3 location you can sense the output inductor current. You can see the output inductor ramping up. So you can use that for picker mode control. But then if we sense number 3, we don't have the information about the transformer magnetizing inductance. So number 3 will help a little bit on imbalance problem, but ideally the best location is still number 2. So there are let's talk about the mode of operation in phase shift full bridge. So at lighter load, people will generally just turn off all the synchronous rectifier FET to save the driving energy. But when the load increase, then we can turn on the FET, the related FET, when the inductor current is ramping up. So when the current going even higher, then during this freewheeling period, if we don't turn on the FET, then there will be current flow through the body diode. And if you are doing a high power design, this body diode loss could be very high. So what people will usually do is we will introduce this mode 2 during this transformer 0 voltage period. We turn on all the FET. So instead of let the current flow through the body diode, we let the current flow through the channel, which will greatly reduce the conduction loss. So previously we mentioned that at the lighter load, one leg is easy to lose substitution, right? So what we can do is, if you reduce the switching frequency, the primary current, peak will be higher, so you will easily to achieve self-switching. And also, we, for example, if you apply the active clamp, then we, with the frequency reduction control at lighter load, we are able to maintain minimum on time so that we can maintain the active clamp operation while in light load. But if you are using gate drive transformer to drive your FET, then this method is not recommended because it might saturate your gate drive transformer. So the other way you can do is doing a burst mode, right, based on the compensation voltage, right? This is a table to compare these two methods, the frequency reduction mode and the burst mode. So basically, the transient response under burst mode, I'm talking about the digital controlled phase shift full bridge. The transient response in using burst mode is expected to be faster because if you use a frequency reduction mode, and it's hard for CPU to follow all these different frequencies, and and the CPU utilization rate will be larger in the frequency reduction mode, but we expect the output ripple under frequency reduction mode will be smaller. Okay, so we have a design that is target to server power, server PSU application, which have 390 volt input, 54 volt output, 3 kilowatt. So here is the waveform of the power supply at the 3 kilowatt and 140 kilohertz switching frequency. Under that condition, we are able to clamp the output rectified voltage at 80 volt. So with active clamp active clamp circuit. So here are the transient response test. So the red dashed line is the spec that we are targeting at, and the result is able to, the transient response is able to meet that NCRPS, by a lot, right? So with a lot of margin. And here's the transient, response. So basically, it's probably taking like 13 to 15 cycles for the currents to stop to ramping up. So we consider it's quite fast. So here's a summary of this presentation. So basically, like I said, the phase shift full bridge is a good candidate for the application that require a wide input and output voltage range and fast load transient response. And I'm talking about the different characteristics among phase shift full bridge converter and other isolated topologies. I'm talking about a principle of operation, type of rectifier, clamping circuit, controls, and showcase with phase shift full bridge reference design. So like I said, this is just an introduction presentation for phase shift full bridge converter. So basically all the what I have been talking about, you can find in the following slides. So there's like powertrain here, different specs. There's a comparison between resonant converter and DAV, resonant converter versus phase shift full bridge, and there's phase shift operation and output rectifiers, and there's a different type of clamping paper. You can look into that, and control paper and design example. So thank you. That's my presentation for this topic. So any questions so far?
네, 질문 있으신 분은 손을 들어주시면 저희가 마이크 전달드리겠습니다. 역시나 한국어로 해주시면 편하게 하실 수 있으니까요. 많은 참여 부탁드리겠습니다. 네, 앞쪽에 마이크 전달드리겠습니다.
Thank you for your presentation. I have a few questions. Firstly, in the phase shift full bridge, the light load is very difficult to achieve ZVS, right?
Yes.
I want to ask your experience based on but at the light load anyway, the output power is low.
Yes.
So even though we cannot achieve ZVS, the power loss, the absolute power loss may not be high.
Right.
So the switching loss may not be high. So probably if we don't care about the efficiency at the light load, then probably the switching loss is acceptable for the MOSFET because maybe the MOSFET will not be heated so much, even
right.
if it has a switching loss, right?
Yes. So maybe, yeah. Let's just look at this. Let's go back to this one, right? So like I said, also in my design example, we are actually using the leakage inductor of the transformer to achieve a soft switching, but at lighter load we are losing ZVS.
Yes.
But in the design, as long as you can make sure your design is your thermal design is good at light load, then it's okay to lose ZVS, right? So you need to kind of a trade-off between what's your design target. If your design target is you need to maintain full range DVS, then okay, then you will need a larger series inductor. But if your design target is okay, light load, I in my design is I can make sure it's thermally okay, but I more care about the heavy load, full load efficiency or half load efficiency. Then you basically can just just to make sure you achieve a soft switching, you achieve ZVS at nearly like 50%, then it should be good.
I ask you this question because the problem of the hard switching is not only the switching loss, but also the EMI or the crosstalk. In here, in the full bridge topology, if in the hard switching, right, we have the high ripple voltage on the VDS, and that high ripple voltage can affect to the VGS. But if the dVdt is very high, dV by dt is very high, it can affect the VGS of that MOSFET, and it can turn on MOSFET unexpectedly.
Yeah.
So we can have the crosstalk, or we can have the shoot-through failure. So I just want to ask your experience at the light load condition. Does that shoot-through phenomena, or does that shoot-through failure happen, or not? Or should we safely say that at the light load condition, if we can accept the switching loss is okay, the crosstalk does not happen?
So basically, even you are at the let me see if there's a waveform. I don't think I have a waveform of that, but if you are say this, let's say this is the how to say, let's say this is the, let's assume this is the primary side MOSFET voltage, right? So if you are losing ZVS, but you are doing hard switching, but because of you still have some current to discharge, so you are not turning on at the 400 volt. You are actually this voltage will resonate low a little bit, then you turning on. So the switching loss, first of all, the switching loss will be lower a little bit, even it's not the ZVS. And the second thing is in our experience, yes, we use TI gain FET for the primary side. So what TI gain FET can do is we are able to adjust the turn on speed. Okay, so if we let the turnaround speed very high, so Ti gain factor can do 100 volt per nanosecond. If we let it switch at 100 volt per nanosecond at low CVS, then yeah, we see the signal being induce low noise and make this crosstalk, this shoot through. So what we do is yeah, you have to lower the switching speed, lower the turnaround speed, then you can reduce this kind of concern.
How can I lower the turn-on speed using the?
So for example, if you are designed with the silicon FET, right? There's a gate resistor. You can increase in the gate resistor to slow it.
The gate resistor, the damping resistor over there.
Yeah. So.
I see. Okay, thank you. And the next question, sorry. The next question is for dual active bridge, is it better than the phase shift full bridge in terms of ZVS operation? The ZVS range is bigger, the DAB?
Let me see where it's So, to be honest, usually those phase shift full bridge and DAB, I often see them being applied to a different application. Both DAB and the phase shift full bridge are using series inductor to achieve substitution, but I think like this one we have in the phase shift full bridge you have the output inductor to do the substitution. So in that sense, in one leg it's easier to achieve substitution than DAB, but we didn't do the apple-to-apple comparison, under the same design spec. It's easier to which one have a wider range that I cannot detail.
Okay. I see. So the Texas Instrument, does they have the controller IC for DAB? Because when I check the reference design, I cannot find out the IC for that. Only using microcontroller.
Yeah, so
right.
We are using microcontroller for the DAB.
Is there any dedicated IC for the DAB?
I'm not aware of any analog IC for DAB, no.
Okay.
Yeah, the control is too complicated.
I see. Okay, final question. So the synchronous rectifier at the output of the phase shift full bridge. If we totally control the synchronous rectifier so that the diode never conducts, only the FET conducts, do you think that we have the peak voltage on the FET, on the output, on the rectifier side? Because as I understand, the voltage peak, the voltage spike on the FET of the rectifier is caused by the reverse recovery current of the diode. So if we operate the rectifier, the synchronous rectifier fully without diode conduction, we will not have the voltage spike on the rectifier. Is it true?
No. So like I mentioned when I talked about this slide. So basically, this model, this spike is I only model this inductor output COSS,